Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 11 of this course. So we were doing this MATLAB simulation of power required curves for at the altitude of 10 kilometers and with compared with the sea level. Alright, so we almost have written the code and we were about to write the plotting commands. Okay, so now let us get back to our MATLAB code. Okay, so here one point I missed to write, that is the velocity vectors. Let me write down here. Velocity vectors. So velocity at sea level is, so let us follow the same command that we have been following up to this session, LINSPACE from 50 to say 350 meters per second and with an iteration of 200. Okay. Now as we already discussed, velocity at 10 kilometers will not be same. Okay. So that you have to mention here V underscore SL into rho SL into in fact square root SQRT square root, alright, into rho SL underscore SL divided by rho at 10 kilometers. Okay, so this is the velocity at sea level. Alright. Similarly, after that we wrote power required at sea level, CL equals to 2W by rho S V square. Then what is the CD at sea level? CD naught plus KCL square. Thrust required at sea level, W into CD by CL, that is at sea level. And then finally power required at sea level, that is power required is thrust required into velocity. This I have divided directly by 746. So what do you get is power in horsepower. Okay. Then what about at 10 kilometers? So we can immediately find, if we know the power required at sea level, we can find power required at 10 kilometers. So power required under PR underscore 10 equals to PR power required at sea level into square root of rho SL divided by rho 10. So since this is a jet aircraft, so hence I have taken this consideration. Okay. So the thrust available was given to us 16,242 into 2. We have two engines. So this is in newtons. The thrust available at sea level can be immediately be found thrust available into rho 10 divided by rho SL. Similarly, power available at sea level, thrust available into velocity, converted that to horsepower at sea level. Similarly, converted this one to horsepower at 10 kilometers. Okay, thrust at 10 kilometers into velocity at 10 kilometers. All right. Okay, and let us see if our code is actually running or not. Let me just run this code. Yeah, so actually it has run. There has been no error. Now let us start plotting these results. Okay. Plotting results. Okay. Now let me write here figure 1. Figure 1. Okay. So this figure 1 will have plot VSL, comma PRSL, alright, okay, comma, let me denote this as by a black line, black, okay, then line width, line width, let us take it as 1.5. Okay, all right, and we want to hold on in the same plot. We want to plot another curve. Okay, so for that we write the command hold on. Now we can write plot V velocity at sea level and power available at sea level. Okay, So V underscore SL, comma, power available at sea level. Alright, now let me denote this or by a black color that is given by K, and the line width, let us select line width to be again same, that is 1.5. Alright, okay. And X label, let us label the X. Okay, so that is velocity in meters per second. Okay, fine. Now we are done with X label. Let's this Y label. In Y, what do we have in Y? We have power. Power in horsepower. Okay. Let me put the title as well. Title is sea level. Sea level. Power required and available. Okay. And let me also put legend here, since there will be two curves in one plot. Okay, so first is power required, all right, which is at sea level, and next is power available at sea level. All right, let me also put X limit over here, 0 to 320. Now quickly go to the figure 2. Okay, so now figure 2 will depict about results of at 10 kilometers. So this is for at sea level, and this is for at 10 kilometers. All right, so now let us write same, almost similar code here. Let me just in fact copy from here. All right, so instead of SL, it will be V underscore 10, PR underscore 10, similarly V underscore 10, PA underscore 10. All right, and the rest also will almost be remaining same. So X label, we have velocity, power is in power in horsepower, and the title is this time 10 kilometers. Okay, 10 kilometers altitude, that is power required and available. So power required, this is at 10 kilometer, and similarly power available at 10 kilometers, and X limit, let us keep it same. So I'm saving the code, and now I'm running it. Let us see if we have any errors. No, so there are no errors fortunately. So this was the power required and available. Okay, ABLE, 1 second. ABALE, okay. Okay, let us save. Fine. So this is power required and power available curve at the sea level. So notice here, the maximum velocity at sea level that can be attained is, okay, approximately you can say 298 meters per second. So when we compare with this at 10 kilometers, then at 10 kilometers what happens? As we discussed, it should be low, and indeed it is actually low, that is the velocity is 291, approximately 291 meters per second. That is the high intersection of power available and power required curve at 10 kilometers. Okay, you can also have a look at the how power available is reduced. Now at sea level, your power is about 12,000 horsepower. Okay, so even at maximum you can see over here, it is in fact 13,000 horsepower. But if you see at 10 kilometers, which is where generally commercial aircrafts fly, so at 10 kilometers your horsepower is now available horsepower is approximately now 4,278 horsepower. Okay, so which was quite expected. All right, so this is how, given the power required available curve at the sea level, you can easily plot the power required and available curve for any given altitude, provided you know the density, and we know the density we can easily calculate from standard atmosphere. Okay, and so this example we considered for the jet aircraft. Similarly, you can plot power required and power available for a piston engine propeller aircraft. So there we have power available equals to neta into P. So the shaft brake power and the propeller efficiency, it needs to be known. So then you can easily plot power available and power required at sea level and at any different altitude. All right, so with this we are covered with this section. Now let us go ahead with the next part of this course, that is the rate of climb. Okay, so let us discuss rate of climb. Okay, so this part is that how fast can an aircraft climb, and how long it takes to reach certain altitude. So for commercial aircraft, they generally fly at 10 kilometers. So how long it takes to reach at that altitude? So that can be determined by the rate of climb. Okay, the rate of climb is nothing but a velocity, that is in meters per second. So to understand rate of climb, let me draw the diagram of the aircraft in a climbing position. So assume this is an aircraft. Now assume this is a thrust, and this is also the direction at which the aircraft is flying, that is the velocity. So this time I have assumed there is no offset between thrust and the velocity, just to make things simpler. All right, now if this is the velocity, then lift will be perpendicular to the velocity. Okay, so this is the lift, and weight will be exactly acting downwards. All right, and remember, what was this angle? The angle between the velocity and the local horizontal. This angle was actually gamma. Okay, now if this angle is gamma, then this angle will also be gamma, and this is actually the drag. All right, so this is also gamma, and this will also be gamma. Okay, so we have considered an aircraft in steady unaccelerated climbing flight. So this is the aircraft that we are considering in steady unaccelerated climbing flight. The velocity along the path is v infinity, and the flight path is inclined to the horizontal at an angle gamma. Okay, now whenever I discuss this climbing with my students, the first question that I ask them, that what do you think is happening to the lift? Lift is actually greater than the weight, or lift is less than the weight during climb phase? Okay, so what do you think? Lift should be greater than the weight, or lift should be less than weight, or lift should be equals to weight? So whenever I ask this question, so most of the time, 99% of the time, I'll get the answer as lift is greater than the weight. Okay, but actually that is not the correct answer. So let us see why. Okay, and let us discuss whether lift is less than the weight or lift is greater than the weight during climb. So for level flight, we know. So level flight that we have studied as of now, lift was equals to weight. Okay, so there is no question in that. All right, and here again the thrust is actually inclined, or thrust is actually assumed to be aligned with the flight path. Okay, now you will get your answer after plotting or writing these equations of motion for this climbing flight. Okay, so let me write summing forces parallel to flight path. Okay, summing the forces parallel to flight path, that is in the direction of velocity. Okay, so here we have thrust, that is in this direction, thrust. All right, in opposite direction we have drag, so T minus D. What about weight? So weight is here having W cos gamma, and this is W sin gamma. So we'll get T minus D minus W sin gamma equals to 0. Why 0? As we are discussing, there is unaccelerated flight, so there will be no acceleration. All right, now you can write this as T equals to D plus W sin gamma. So let us take this as equation number 1. Now write summing forces perpendicular to flight path. All right, so what are the forces which are acting perpendicular to flight path? One is lift, which is exactly at perpendicular to the flight path, and W cos gamma, which is acting at the opposite direction. Okay, so you can write here L equals to W cos gamma, that is equation number 2. Okay, now if you focus on this equation carefully, that is L equals to W cos gamma, your lift has actually reduced. Okay, so this is cos gamma. So gamma will be how much? So maybe 5 degrees, or maybe 10 degrees, 15 degrees. Okay, so at small angles your cos gamma will be approximately what, equals to 1. Okay, so it is actually will be reducing your lift. So lift will be actually less than your weight. Okay, then how the aircraft is able to still climb if lift is actually less than the weight? Okay, how the aircraft is able to climb? Okay, so that answer you will get it if you focus on equation number 1, so that is T equals to D plus W sin gamma. All right, so thrust is not only working to overcome the drag component. Okay, thrust is not only working to overcome the drag component, it is for climbing flight, it is also supporting a component of weight. Okay, so from this equation number 1, thrust is not only working to overcome the drag, but it is also supporting some component of the weight. So what is the weight component? W sin gamma. Okay, so during climb your thrust is a very important parameter. Okay, if you have sufficient thrust, only then the aircraft will be able to climb. All right, so always remember, during climbing flight, lift is actually less than the weight. Okay, then what compensates? Thrust actually compensates the weight component. All right, now equation 1 and 2 are called equations of motion for climbing flight. Alright, previously we had written equations of motion for steady level flight, and now these equations 1 and 2 are the equations of motion for applicable for climbing flight. Alright, now what we'll do is we'll multiply equation 1 by v infinity on both sides. Alright, so what do we get? This is the equation 1. So that is t into v infinity equals d into v infinity plus w into v infinity sine gamma. Okay, let me write over here t into v infinity. Now I'm writing infinity. So please assume it is always a free stream velocity. Okay, t into v infinity. I have taken to the other side dv infinity plus w v infinity sine gamma. So now I can write here tv infinity minus dv infinity divided by w equals to v infinity sine gamma. Alright. Now what is this v sine gamma? So from the figure we know that aircraft is actually going in this direction, and this is the v, okay, and this is the gamma. So if you resolve these components, this will be v cos gamma and this is v sine gamma. Okay, so this v sine gamma is actually responsible for your climb, that is the vertical velocity. Okay, so this is v sine gamma. This v sine gamma is the vertical velocity. Okay, this vertical velocity is called rate of climb. V sine gamma, this is rate of climb, and usually we denote it by r by c. So if I write r by c anywhere, it means I am writing rate of climb. Okay, so now rate of climb equals to v infinity sine gamma equals to t v infinity minus d into v infinity upon w. So this is equation number 3. Now if you focus here, so this t v infinity is what? T v infinity is actually your power available, है so power available, and dv infinity is power required. Remember d was equals to tr, so this is power required, okay, for level flight. So it can be assumed for climbing flight, since gamma is less than 20 degrees, so this tv that we can assume this is as power available and dv is power required. Okay, so that means power available minus power required. So that means what? This is nothing but the excess power. Alright, so tv minus dv is nothing but the excess power. Alright, so rate of climb I can write here as excess power divided by w, that is weight of the aircraft. Alright, so if I have drawn these curves multiple times, so let me draw again, that is power with velocity. So this is for power, this is the power required, and this is the power available. Okay, this is for which engine? This is for propeller driven. Okay, this is for propeller driven, and see here at this velocity we have maximum excess power. Okay, this is excess power, in fact maximum excess power. Alright, similarly if I plot it for power with velocity for jet aircraft, this was the power available and this is again the power required. So here this is the maximum excess power. Okay, so clearly rate of climb depends upon the raw power in combination with the weight of the aircraft. So which was quite intuitive as well. So higher the power, so if we have higher the power, better the climb performance. Better the climb performance, which is again intuitive as well. Alright. Okay, so now let us proceed further. So what was lift here? Lift was equals to W cos gamma. Alright, so for climbing flight, less lift is needed for climbing when compared with the level flight. So if CL is less, then obviously CD also will be less. So if CL is less, then CD also required will be less. Okay, so then drag will also be smaller when compared with the level flight, because in level flight lift is equals to weight. Please understand, in the level flight lift is equals to weight of the aircraft. Okay, but during climb lift will be less than the weight, and also the drag will be less, okay, when compared with the level flight. All right, now to make this point even more clear, let us consider the weight of an aircraft as 2000 approximately kgs, 2000 kgs, area as 30 meters square, CD naught as 0.015, Oswald efficiency factor as 0.6, aspect ratio equals to 6, and if we consider velocity as 100 meters per second traveling at sea level, then what will be the CL? CL will be nothing but 2W by rho v square s. So we write here 2 into 2275 divided by 1.225 into 100 square into 30. Okay, so this will again yield wrong results, as I have explained the previously as well. CL is actually a dimensionless quantity. This weight, this has to be written in newtons. Okay, you have to multiply by 9.81, otherwise definitely you will get wrong answer. So most of the students will commit mistakes here. Alright, you need to understand what unit are we talking about. Okay, so CL is 0.1214. Then we can easily find CD, that is CD naught plus KCL square. So CD naught is 0.015 plus K is 1 by pi E AR, pi E into 0.6 into aspect ratio 6, pi E AR into CL square. So CL is 0.1214 whole square. So if you find this, you will get 0.016. Okay. Now this was for level flight. What about climbing flight? So for example, if the aircraft is climbing, say maybe gamma equals to 30 degrees. Okay, let us consider 30 degrees to demonstrate our point. Okay, again at sea level. So then CL, you can find CL equals to, this time CL will be 2W by rho v square s. Is this correct? No, this is not correct. Okay, so during climb we have L equals to W cos gamma. So we will have here W cos gamma. All right. So now if you substitute gamma 30 degrees and calculate accordingly, you will get CLS 0.1051. Okay. So now the CL has actually reduced. Previously CL was 0.1214. All right. Similarly CD. So CD you can find CD equals to 0.015 plus 0.1051 square by pi EAR, pi into 0.6 into aspect ratio 6. So this comes around 0.015. Okay, so previously drag was 0.016, so this is 0.015. Okay, so this has started reducing. Okay, even if you consider the flight path angle as even 30 degrees. Okay, fine. So the point here, the note here is CL for climb will be less than when CL for level flight. Please never forget this point. Similarly, CD for climb will be less than CD for level flight. Alright, Now generally speaking, for example, for different types of aircrafts, for example, this different type of aircraft, what is actually the typical flight path angle? So these are estimates. Okay, so for commercial aircrafts, okay, so typical flight path angle will be 10 to 15 degrees. Okay, so for fighter aircrafts, it can go to 30 degrees to 60 degree. It can even go beyond this. Okay, for trainer aircrafts, so trainer aircraft, it will be 15 to 25 degrees. What about vertical takeoff? So obviously it can go up to 90 degrees. Okay, so these are the rough estimates of different types of flight path angle for different aircraft types. All right. So also for jet and propeller aircraft, there is some velocity at which excess power is maximum. So let me draw the plot again. Let me write it here. When do we have this R by C maximum? R by C will be maximum when we are talking about maximum excess power divided by W. Okay. So remember this figure. So this is the velocity. So this is the velocity at which R by C is maximum. So let me plot the curves here. That is the power. This is the velocity. This is the power required. This is the maximum power available. Alright, so this is the velocity at which we have maximum excess power. Alright, so this will be again at a particular altitude. So as I explained in the previous class. Alright, now let me plot another curve. Alright, depicting in the y-axis will have rate of climb. Okay, or the vertical velocity, rate of climb, and here we have the same velocity. Okay, now this was the point at which the velocity was maximum, power available equals to power required. Okay, now what will happen to the rate of climb at maximum velocity? So at rate of climb, at maximum rate of climb will be, so how much do we have excess power at this point at maximum velocity? So excess power is 0, right? So your rate of climb will actually be 0 at this point. Okay, and the maximum, when is the rate of climb maximum? It is maximum at this point. Okay, at this point. So your curve will actually be something like this. Alright, and this horizontal tangent will define your maximum rate of climb. Okay, so this was actually V max, and this is the velocity at which R by C is maximum. Okay, and this is the horizontal tangent which is defining where is your rate of climb maximum. Okay, so it is maximum at this point when we have maximum excess power. Okay, so maximum excess power yields R by C maximum, rate of climb maximum. Okay, so this is another way of pointing or finding out the maximum rate of climb with velocity. So their horizontal tangent defines the point of maximum rate of climb. Okay, so as mentioned earlier, the velocity at power available and power required curves intersect at maximum velocity, which is this one. okay, for a steady level flight. So here no excess power is available exist at Vmax, okay. So at this point, what do we have? At this point, we have R by C is 0. That means aircraft cannot climb beyond this point at V maximum. Alright. So another useful way of plotting these or finding maximum rate of climb is the Hodograph diagram. Okay, Hodograph diagram. Now what is this Hodograph diagram? This diagram is the plot between the horizontal component of velocity and the vertical component of velocity. Okay, the vertical component of velocity is nothing but rate of climb, and here we have horizontal component of velocity, that is Vh. Alright, so here also you will get similar plot. Okay, here also you will get a similar plot. Alright, here the horizontal tangent will define your maximum rate of climb. So just to be clear, this is the velocity vector, okay, and this was gamma. So this is the horizontal component of velocity, that is Vh, and this is the vertical component of velocity Vv. Vv was equals to rate of climb or V sine gamma, and this is the horizontal component of velocity. Okay, so this figure we call it as a Hodograph diagram, where again this tangent is defining maximum rate of climb. Okay, now often I ask students this question, that if I draw a line which is actually intersecting here, so what does this represent? Now if this is a horizontal component of velocity and this is a vertical component of velocity, what will this line represent? Okay, so this line is actually the velocity vector, okay, which is nothing but the horizontal component of velocity is in the x-axis, vertical component is in the y-axis. Alright, so let me define this as a point A, let me define this as point B, and let me define this as point C. Okay, fine. Now this is the velocity, this is the gamma. Alright, okay. Now what we'll do is, at maximum rate of climb, let me ask you, at maximum rate of climb, will gamma be maximum? So at maximum rate of climb, will gamma be maximum? Okay, so if you see this figure carefully, gamma will not be maximum at maximum rate of climb. When is the gamma maximum? Gamma is maximum at point C. Okay, at point C we have gamma maximum, and where we have maximum rate of climb? Maximum rate of climb is at point A. Okay, so this is where we have maximum rate of climb. Alright, so this is gamma maximum. Alright, so even if you draw a line over here till point A, so that will not be your gamma maximum. Okay, so point A defines, let me write over here for notes. So point A defines R by C maximum, that is horizontal tangent to the hodograph. Okay, now what did we do? We considered a velocity vector from the origin which is intersecting hodograph at point B, which is at an angle gamma with respect to horizontal. Now what if we, now as this velocity is rotated counterclockwise in this direction, the rate of climb actually first of all is increasing. It becomes maximum at point A and then finally decreases. So at point C line becomes tangent. Okay, so this line is becoming tangent, and this tangent line becomes the maximum climb angle. Okay, gamma maximum, for which the aircraft can maintain steady level flight. All right. So now the point here is the maximum rate of climb does not occur at maximum climb angle. Okay, intuitively it may look like the maximum rate of climb is happening at maximum climb angle, but that is not the reason. Okay, because of the reason that I have just explained now. Okay, so maximum rate of climb does not occur at maximum climb angle. Now let us consider the same aircraft that we discussed till today, and we'll calculate rate of climb versus velocity at sea level for the same aircraft. All right. Okay. Now let us find the rate of climb. Now consider velocity as 150 meters per second. Say for example, consider velocity 150 meters per second. So rate of climb equals to power available minus power required by W. All right. Now here, what is rate of climb actually? It is climbing the altitude at a certain amount of time, right? So this is nothing but the velocity at which the aircraft is climbing. Okay, the vertical velocity, and the velocity unit is obviously meters per second. Now what units will you put in here to get meters per second? Okay, that is the question that we need to address. So consider now power is in horsepower. Okay, this is in horsepower, and the weight is in newtons. Okay, the weight is in newtons. Now what will you do? Convert that to watts. So 746 watts, 1 horsepower equal to 746 watt. Here we have newtons. And what is watt? 1 watt is 1 Newton meters per second. Okay, so you will get 746 Newton meters per second upon newtons. Okay, so you will get, so you have to multiply this by, so power available minus power required by W, multiply this by 746. So finally you will get answer in meters per second. Okay, now generally rate of climb we can also find in meters per minute, so that gives us more intuition. So just converts these seconds to minutes. Okay, so now in the numerator you have to multiply by 60, not in denominator. Okay, please do not commit that mistake. So in numerator multiplied by 60, since the second was in the denominator. All right, so now we have meters per minute. All right, so finally rate of climb equals to power available minus power required upon W, just multiplied by 746 multiplied by 60, you will get meters per minute. Okay, fine. Now we considered 150 meters per second, right? So power available was thrust available into velocity, and how much was the thrust available? 32,485 into 150. We consider 150 meters per second. Okay, so this comes around 487,2750. Now what is this? Newtons meters per second. Newton meters per second or watt. Now we'll divide it by 10 to the power minus 3 to get kilowatts, or you can convert it to horsepower. Okay, we'll divide it by 746. So when you divide by 746, you will get 6,531.83 horsepower. Okay, 6,531 into, that is the horsepower. Now what will be the power required? Now let us see what is the power required. Okay, so this, remember, we have already drawn the figure of power required with velocity. All right. So at 150 meters per second, what is the power required? Let us see through our plots. So this is the code that we have written in the previous lecture. All right, so let me run this code. And this was applicable for sea level as well as at 10 kilometers. Let me run this code. So currently we are dealing with the question for sea level. Let me go to the sea level plot. So we considered velocity as 150 meters per second, and let us see what is the power required at 150 meters per second. Okay. Okay, so we are getting almost around, yeah, we are getting almost 1790. So let us consider 1800 horsepower is power required at sea level. Okay, let me go back to the slide. So power required we are getting here as 1800. Okay, approximately 1800 horsepower. All right, at 150 meters per second. Now finally we can find the rate of climb equals to 6531.83 6531.83 horsepower. That is power available minus power required. Let me write here minus 1800 divided by the weight 88176.75. Now taking care of the units, multiply by 746, multiply by 60. So finally you will get approximately 2400 meters per minute. So this is the rate of climb that you will get, 2400 meters per minute. Okay, so now let us see in the plot, are we getting the similar results or not? Okay, now let us go to the plot again. All right, so what we need to do here, we need to modify this code and add another few lines related to rate of climb. Okay, so we did here till power available at sea level as well as 10 kilometers. Let us also plot rate of climb at sea level. At sea level, then let us write here as meters per minute. Okay. So RC rate of climb, let me denote this by SL. RC rate of climb at sea level is given as power available minus power required. Power available minus power required. Power available minus power required. Okay. Divided by W. Divided by W. Okay. This is element to element multiplication. That's why I've written dot. Okay. Now you have to take care of the units into 746 into 60. All right. Okay. Similarly, you can also see, since we are already plotting at sea level, let us see the rate of climb at even 10 kilometers. Okay. 10. So power available at 10, power required at 10. All right. This is finally multiply 746 multiply by 60. I am saving this. Now let us go to the plotting of results. So let me write here. Now let us plot rate of climb. So figure 3 is rate of climb. Okay. Consider this as figure number 3. Consider this as figure number 3. And Let me write here plot velocity with rate of climb. All right, so velocity underscore SL comma RC underscore SL, fine, comma, let me denote it as with R, and the line width is again 1.5. Line width as again 1.5. Okay, this is the plot, and X label is the velocity in meters per second. Velocity in meters per second. And Y label rate of climb meters per minute. Let me write the title. Sea level rate of climb versus velocity. Rate of climb versus velocity. Okay. Let me again keep here as grid on, and let me again define the limits in the x-axis, which is 0 to, let us consider 320 this time. Okay, let me save it and let us see if there are any errors. All right, so this is how it looks like, the rate of climb. All right, which is rate of climb in the y-axis, and in the x-axis we have velocity. So what did we find in our relations? So at 150 meters per second, so in around 150 meters per second, our rate of climb was this is 2395, approximately 2400. Okay, so that is, let us see how much did we get over there. Yeah, so this is approximately 2400 meters per minute. Okay, so whatever we did there, it is actually making sense, and we have got approximately the similar results. So at 150 meters per second, we have approximately 2400 meters per minute as rate of climb. Okay, now we can also do one more thing. All right, let us plot Hodograph at 10 kilometers. 10 kilometers. Okay, now what we'll do is we'll assume a realistic constant climb angle. Constant climb angle of 5 degrees. Okay, now consider gamma in degrees equals to 5. Okay, now we have to convert this to radians. So gamma equals to degree to radians, TEG to radian. All right, this is gamma underscore degree. Fine. So we can also mention here horizontal component of velocity, Vx equals to V underscore 10. All right, dot into cos of gamma. Okay, now let us plot the figure 4. So plot Vx comma rate of climb underscore 10. All right, comma Here let me denote it by m with the line width of again same line width of 1.5. Okay, then x label as horizontal velocity, comma v underscore x, that is meters per second, and similarly y label, in y label we have vertical velocity, at v underscore y, convention meters per second. All right, and then the table or title convention, I'm using new command over here, sprintf. I'm writing here hodograph, sprintf hodograph, again brackets. So let me write here gamma equals to percentile 0.1 f. All right, we close this bracket. All right, so I have written this title as sprintf hodograph gamma equals to plus percentile 0.1 f, that is up to particular decimals. Okay, next grid on, and let me put the limit over here, while limit 0 to 700. Okay, now let me save this first and let us see the hodograph plot. All right, now see here, so in figure 3 we have plotted rate of climb with velocity. Okay, now we have horizontal component of velocity, and here we have vertical component of velocity, and this is at gamma equals to 5 degrees. Okay, so this looks almost similar curve, that is in the hodograph. All right, so now we are done with this rate of climb, even the expressions as well as the MATLAB simulation. In the next lecture we'll be talking about the gliding flight, that will be without or no thrust at all. Okay, thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said but also in what remains unsaid. Today I'll be reading one of the shortest instances of a short story that I have ever encountered, and indeed the very charm of this particular story that I'm going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I'll be reading out is perhaps the closest to the one that Maugham wrote. The story is titled, in all of its adaptations almost, as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samara and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samara to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.